In this video, I will show you how to find the interval of convergence for a given power series. To find the interval of convergence means to find the values of x for which the given series converges. And to do that, we are going to use the ratio test. So we're going to set up the following limit. So we're going to set up the limit of the ratio of a successor over predecessor. And in the numerator, I'm going to write the successor. That is, I'm going to write the expression, but instead of n, I'm going to write n plus 1. And in the denominator, I'm going to write the general term. So I'm just going to copy everything over. And now we are going to simplify this expression and write it as a single fraction. So we're going to have -1 to the n, 2 to the power n plus 1, x to the power n plus 1, over n plus 1, that's the numerator. And now dividing by the denominator, so we have -1 to the power n minus 1, 2 to the n, x to the n, and n goes to the numerator. Now we can simplify this further. So -1 to the n is irrelevant when we have absolute value. 2 to the power n can reduce this 2 to the power n, and x to the power n can reduce this x to the power n. So what's left in the limit is the following. We still have absolute value of x. We have 2n over n plus 1. Now, absolute value of x can be factored out of the limit, and this limit right here is just 2. So what we have is 2 absolute value of x, and in order for the series to converge, the limit of the ratio must be less than 1. So this gives us a simple compound inequality. So absolute value of x must be less than 1/2, and solving it gives us the following solution. So x must be between -1/2 and +1/2. That means for all x values between -1/2 and 1/2, this given power series converges. Well, what happens at -1/2 and 1/2? To figure that out, we're going to plug in x equals -1/2 into the series and figure out whether it converges or diverges. So when I replace -1/2 into this series, -1/2 and 1/2 can be separated. So we have -1 to the n, 1/2 to the n over n. And we see here that -1 to the n minus 1 times -1 to the n together is -1 to the power 2n minus 1. 2 to the n times 1 over 2 to the n is just 1. And it appears to be an alternating series, but actually 2n minus 1 is always odd, and -1 to the power that is odd is always -1. So here we have a negative harmonic series which diverges, and to be precise, it diverges because it's p series. P equals 1, which is less than or equal to 1. So at -1/2, the series diverges, and -1/2 therefore is not in the interval of convergence. So next we're going to check the series at 1/2. So replacing 1/2 for x in the power series gives us the following series. 2 to the n and 1/2 to the n, actually the product is equal to 1. And here we do get a true alternating series which converges by the alternating series test. So that means the original power series converges at 1/2 and diverges at -1/2. So we write our interval of convergence as from -1/2 excluding -1/2 all the way to 1/2 including 1/2. So this is the interval of convergence for the given series.